Hello and welcome to Living Proof, the Isaac Newton Institute podcast. My name is Dan Aspel. Today we bring you a very special episode on a very significant date. That's because the 23rd of June 2023 marks exactly 30 years since Sir Andrew Wiles announced his first proof of Fermat's last theorem. This took place in I&I's main seminar room during one of the first programmes ever hosted at the newly opened institute. The fascinating documentary you're about to hear has been a collaboration with our colleagues Marianne Freiberger and Rachel Thomas at Plus magazine. You can find the same content hosted via their Maths on the Move podcast on plus.maths.org and on Podbean. On their same website and on our own newton.ac.uk, you will find an in-depth article accompanying this podcast, embedded in which you can watch a short but we hope affecting video interview with Andrew Wiles, which we recorded on the same day as this documentary. That's enough introduction for now. I shall leave you with the man of the hour. We hope you enjoy what you are about to hear.
I am Andrew Wiles, and Fermat's last theorem was a statement or a claim by Fermat in the 17th century that there are no solutions to the equation x to the n plus y to the n equals z to the n, where x, y and z are integers and n is at least 3.
That was the voice of mathematician Andrew Wiles, famous for proving one of the most infamous results in mathematics, Fermat's last theorem. Exactly 30 years ago, on the 23rd of June 1993, he announced his proof of this result at the Isaac Newton Institute in Cambridge. In this special episode, we'll hear from Andrew Wiles and other mathematicians about the importance of this result and the importance of this anniversary.
Welcome to the special joint edition of the Living Proof podcast from the Isaac Newton Institute and the Maths on the Move podcast from plus.maths.org. I'm Marianne Freiberger.
And I'm Rachel Thomas. For this podcast, we, along with our good friend Dan Aspel from the Isaac Newton Institute, were lucky enough to talk to Andrew Wiles in his academic home at the University of Oxford.
And we also spoke to our colleagues Tom Kerner and Jack Thorne from the Faculty of Mathematics at the University of Cambridge. Before we delve into the details of Wiles' amazing and inspiring story, let's have a look at the famous theorem that lies at the heart of it. Let's start by considering an equation of the form x squared plus y squared equals z squared. The question is, Rachel, can you find 3 non-zero integer solutions, so that's whole number solutions, x, y and z, which satisfy the equation?
Well, I know from Pythagoras' theorem that if I have a right-angled triangle with a length of side x, a length of side y and a hypotenuse of length z, then x squared plus y squared equals z squared. So I know there's definitely some solutions. And actually, I happen to know there's a whole number solution if you have a triangle with a side of length 3 and a side of length 4. The opposite side will have length 5 because 3 squared plus 4 squared equals 5 squared. And actually, I think another solution is 12 squared plus 5 squared equals 13 squared. So I've definitely got at least 2 solutions to that equation.
And it actually turns out there are infinitely many integer triples, known as Pythagorean triples, which satisfy the equation. Tom Kerner of the University of Cambridge, who had the pleasure of witnessing Andrew Wiles announcing the proof of Fermat's last theorem 30 years ago, takes up the story of this interesting result.
So with squares, you have a lot of formula of the form 12 squared plus 5 squared equals 13 squared, and so on and so forth. And people naturally asked, can we do the same with cubes? So you look at it and you try it, and it don't work. Fermat, in one of his notes in an ancient Diophantus book on equations, says there doesn't exist such a relation for cubes or for fourth powers or indeed for any other powers, but unfortunately the margin is too short to contain my proof. And nowadays we suspect that he didn't have a full proof, but that he may have had a proof for some powers. And this hypothesis became more and more famous, and it was, I think it's fair to say, the most famous problem in mathematics.
Fermat made the infinite note in his mathematics book in 1637, so there was a lot of time indeed for the fame of this unproven claim to build up. And it was over 300 years after the famous scribble that Andrew Wiles came across Fermat's last theorem at the tender age of 10.
Well, I first found out about Fermat's last theorem from the cover of a book by E.T. Bell when I was about 10 years old. I got it out from a public library, and the whole book was about the problem, and it advertised the famous prize, and it talked about the attempts that had been made to solve it. And I was just captured by the romantic history of it. So I spent some of my teenage years and even in college trying to solve it, and I even thought I'd solved it once and showed it to my tutor and so on. But then when I became a professional mathematician, I realized this was not something you should work on because it probably wouldn't generate any results. Even failed attempts weren't that interesting anymore.
But Fermat's last theorem did not let go of Andrew Wiles. Sometime later, after significant progress was made in some relevant mathematics in the mid-1980s, which we'll hear more about in a moment, he started to work on Fermat's last theorem again. Amazingly, he decided to do so on his own and in secret, which seems to us an unusual thing to do since mathematics is often a really collaborative subject. And not only did he work on it on his own, he also worked on it for a very long time of 7 years.
Funny enough, very few people want to work on a problem for that long. They might think about it on and off when they're doing the rest of their work, but actually to really commit yourself to a problem, it takes a certain kind of personality. And also I didn't really talk about it because I did initially a tiny bit, and then I realized it got just so much unwanted attention. If you say you're working on it, you wouldn't be left in peace. So I felt it was wiser to do it in private.
I think the first time I became aware of it was when I was doing my A-levels and I was getting ready to apply to university and thinking that maybe it was worth studying maths at university. And I wanted to do a bit more reading just to kind of illustrate how keen I was. And I picked up a few books, and one of them was Simon Singh's book, Fermat's Last Theorem, which I think probably for many people is where they first became aware of the subject. And I think I found that quite exciting, actually, because, doing A-level maths, you learn how to do certain kinds of calculations and how to balance two balls on a rod and things like that. But this was the first time that I'd seen a kind of really human story attached to a mathematical problem. And not just, a story of one person, but, people kind of somehow speaking to each other over a period of centuries. But that I found quite exciting.
That was Jack Thorne of the University of Cambridge, who was 6 years old when Andrew Wiles announced his famous proof in 1993. Jack Thorne is an expert in the field of mathematics that builds on the proof of Fermat's last theorem, and he helped us to trace the main steps of the proof, which, even as mere mortals, we can follow, although the proof itself was over 350 years in the making.
The first kind of really significant element of the story is this idea that you can take a putative solution to the Fermat equation, and you want to prove that no such solution exists. So you do this typical thing in mathematics where you say, well, let's suppose it does exist, and then let's try and derive a contradiction from that. One thing you can do is try to take such a putative solution and then write down other mathematical objects that might be of interest. And the thing that does the trick is this so-called Frey elliptic curve. So it's another equation you can write down using this solution. And the basic idea is that this elliptic curve, whatever it is, should have properties that are so strange that it can't possibly actually exist, and that's your contradiction. But then you have to say, okay, well, what does it mean, strange? How am I going to prove that it doesn't exist? And then there's an extra step you have to take, which is connecting with what
a priori might seem to be a whole other part of mathematics, which is the world of modular forms. So these are other kinds of objects that come from analysis, and they have different kinds of symmetries to the symmetries enjoyed by elliptic curves. But in the second half of the 20th century, a series of mathematicians, the names that are normally attached to it in chronological order are Taniyama, Shimura, and Vey. A series of mathematicians had suggested that to any elliptic curve, such as the one that you might write down starting with a solution to the Fermat equation, you can associate a modular form, and people nowadays call this the modularity conjecture. And prior to Wiles's work, it had been proved that if you can prove this so-called modularity conjecture, so if you can make this bridge between the world of elliptic curves and modular forms, that allows you to kind of quantify strangeness of elliptic curves in a way that is sufficient to kind of solve the Fermat problem.
Okay, that was quite a lot of information. Why don't we do a quick recap? So the aim is to show that there are no non-zero integer solutions to the Fermat equation, that's x to the n plus y to the n equals z to the n, for any exponent n greater than 2. Marianne, what happens next?
Okay, well, next, in typically mathematical fashion, what you do is you assume that there is a solution and see if you can derive a contradiction from that assumption, which then proves the assumption is false. Now, it turns out that from Fermat's equation, x to the n plus y to the n equals z to the n, you can build another equation involving cubic powers of x and y, which is known as the Frey curve, named after the mathematician Gerhard Frey. It's an example of an elliptic curve. So people believed that to any elliptic curve there should be associated another object known as a modular form. Now, we won't go into what a modular form is here, we just accept that there should be such a modular form connected to each elliptic curve. And the fact that there should be this connection between elliptic curves and modular forms was the famous modularity conjecture. Now, in the mid-1980s, work by the mathematicians Jean-Pierre Serre and Ken Ribet showed that if Fermat's last theorem were false, meaning that there are integer solutions to Fermat's equation, then the Frey curve would be so weird it couldn't possibly come with an associated modular form.
So that's where the contradiction comes from. So if you could prove the modularity conjecture, saying that there is indeed a modular form for every elliptic curve, then you would have shown that this weird Frey curve couldn't possibly exist. Because if it did, then it would have no associated modular form. Therefore, the solutions that we assumed to Fermat's equation can't exist either, which renders Fermat's last theorem true.
That's exactly right. And it was the work by Serre and Ribet in the 1980s that got Wiles' hopes up that Fermat's last theorem could be proved. Here he is again taking up the story.
So in about 1984-85, Gerhard Frey made a proposal for how to attack Fermat's last theorem using more modern mathematics. And it wasn't quite right, but it was subsequently clarified and developed first by Serre in the form of a precise conjecture, and then by Ribet in 1986, actually showing that definitively Serre's conjecture would imply Fermat's last theorem. So I'd been skeptical when the first announcement came out, but when Ribet proved this connection, I was completely hooked, and I just dropped everything and started working on Fermat right away. I mean, at first, even given this translation into a well-known problem at the time, this problem of modularity, no one had any idea really how to approach modularity. Or I could say, in some sense, people had too many ideas. It wasn't even clear which branch of mathematics it should be approached from, because you could describe it in terms of analysis, in terms of geometry, or in terms of arithmetic. One could formulate in each of these different domains. So it wasn't clear which kind of technique was going to be useful for it. So initially, all I was doing was trying to find really a point of view, a way to actually think about the problem. And I was drawn to some ideas that Mazur had in a different problem some when I'd been at Harvard some years before. And I tried to approach it from that angle, and it gave me a way, and then of thinking about it, and then it developed a bit, and then I changed the way, but it gave me just the first toehold. And from that point, I kept feeling I was making some kind of progress. I mean, whether it was going to converge to an answer or converge to some other unsolved problem, I didn't yet know.
Eventually, however, Wiles did find a proof of the modularity conjecture, which then implied that Fermat's last theorem was also true. And he announced it on the 23rd of June 1993 at the Isaac Newton Institute in Cambridge. Now, this was a monumental announcement, and we'll hear from Tom Kerner again. Tom was lucky enough to be present at the announcement, even though he works in a completely different field of mathematics. And as Tom explains, Andrew Wiles was giving a series of lectures over 3 days at the Isaac Newton Institute, and no one knew that Andrew Wiles was about to announce the proof.
Rumours started to get around. Andrew Wiles was giving 3 lectures, and I do not know if some people knew or some people just speculated, but I asked one of Andrew's students, and he said he couldn't say. So I said, well, would I regret missing the lecture? And he said yes. So I formed part of a fairly large crowd, big lecture theatre, even more than in most lectures, the experts at the front, and then the less expert, and then the hoi polloi crowd of people who'd come just in case. And yeah, I think the atmosphere was electric. Didn't understand anything of the lecture, as indeed I expected. There'd been 2 lectures before, and really mathematics is very hard, and unless you think about it a great deal, you do not expect to understand something, particularly something as abstract as that. And at the end, Andrew wrote up the statement of Fermat's last theorem, and indicated that what he had done, he felt, proved it. There was tremendous applause. Then the experts got up and asked questions, which indicated that although the details of the proof remained to be thoroughly checked, it was at least a very plausible way of attacking the problem, and also a new way of attacking the problem, so that whether it succeeded or not, it really had added a very substantial amount to mathematics.
Here's a description of the experience from Andrew Wiles' point of view.
On the one hand, I was very excited to present it, but there's also a feeling you're releasing it, and there's always a tension the first time. You've been thinking this out, a lot of it on your own. You want to feel you haven't done anything stupid. No, I think people want to see the details, but they could see that this was a completely new approach, and that it was going to prove something. Whether it had all the details of the final claim remained to be seen.
The desire to see the details of the proof was justified. It turned out that the proof had a hole, which it took Wiles, together with mathematician Richard Taylor, almost a year to fix. But then, finally, in 1994, the proof was complete, and the centuries-old problem, inspired so tantalizingly by Fermat, with a note in the margin of a book, had finally been solved.
You might think that Wiles's proof finally laid this area of mathematics to rest, closing a door on the mathematics that had been developed to solve it. But this wasn't the case at all. In fact, as Wiles tells us, it was quite the opposite.
That's the very strange thing about Fermat's last theorem, is that, yes, it had a romantic history, and it was, people wanted to do it for that reason. But twice in history, not just once, but twice, progress on that problem, specifically working on that problem, has opened a huge new door in mathematics. I mean, some problems you just solve them and, okay, you found a solution, but that's the end of the problem and the history is closed. So the history is now closed on this problem. But these two doors it opened, the first one in the 19th century, when it basically initiated my field, because Kummer's attempts to solve it in a completely different way led to the whole construction of ideals in number rings and to the general ideal class groups and just the whole of basic arithmetic of my field. And then it happened again. So that made progress on the problem, but on the original Fermat problem, it solved many cases, but it did not solve the general case. And then the problem went dormant for a long time. And then after Fry, Sayre and Ribbit, it opened up again. And now it's opened another door, and this time on all these problems of modularity and so on. Now, these problems of modularity are just the sort of one more door opening on this great perspective of what's called the Langlands program. And that's the future of mathematics.
As Wiles explained to us, it's difficult to explain the Langlands program even to an expert, so we won't attempt it in this podcast. Suffice to say that it consists of a web of far-reaching conjectures made by Robert Langlands in the 1960s that draws extremely surprising connections between different fields of mathematics. Proving all these conjectures is seen by many as the single biggest project of modern mathematics. In particular, Langlands tells us that the area of modular forms provides tools for attacking problems in number theory that are more akin to what we know from calculus. Here is Andrew Wiles again.
What Langlands brought in was the understanding that actually there's an almost deeper connection with actually functions that arise more in calculus. So, and he says, actually that will give you a key to solving some of these number theory problems, that actually their answers are coded in this much more analytic and sort of calculus-based mathematics.
Jack Thorne told us about the bridge that the Langlands program provides, which takes us from number theory to a very different world, the maths of generalizations of modular forms.
And there are two worlds which, a priori, it's not clear that they should be connected, but in fact they talk to each other in ways that are at once kind of very mysterious, but kind of very striking in terms of how closely they are connected. It's really like there's a hidden telephone line. You can make very precise predictions about what's going to happen in a certain number theoretic question, and then you can kind of do some computations about that question on the computer, and then it turns out your predictions were kind of 100% accurate. I mean, it's kind of amazing, actually.
Jack Thorne is a leading expert in the field. He works on the Langlands program, and he also works on questions surrounding generalized versions of the Fermat equation and similar equations.
Well, most of my work these days is in the Langlands program, and you might say somehow directly inspired by these techniques that were introduced to study the Fermat equation. I've done a lot of work towards proving modularity of elliptic curves in more general settings. One setting that's quite interesting is if instead of thinking about as you do classically, solutions to equations like the Fermat equation with integer or rational number coefficients. What if you start thinking about solutions in some other number system, like if I, instead of taking numbers a, b, c, which are integers, maybe I might take numbers a, b, c, which are integer combinations of integers and the square root of 2, for example. How do things change if I throw in something like the square root of 2? And it turns out that there's a whole beautiful theory that exists and that generalizes the classical setting.
So what's the analog to Fermat's last theorem if you say throw in the square root of 2?
If you take one of these so-called number fields, that's this generalized number system, I think it should be true that there's no solution to a to the b plus b to the p equals c to the p as long as p is a large enough prime number. But we don't know how to prove that. We only know how to prove that if we kind of assume various conjectures coming from the Langlands program. This is like a future dream that we'll be able to prove such results unconditionally, but we can't do it at the moment.
So Andrew Wiles' proof of Fermat's last theorem settled a problem that is so easy to state that even a high school student can understand it. Yet it has opened a door onto a deep area of mathematics, which Jack Thorne believes will see exciting developments in the next decade or so.
Fermat's last theorem has definitely defined Andrew Wiles' career. He is one of the few mathematicians who is well known outside of mathematics. Within mathematics, he has received a wealth of honours and awards, including the prestigious Abel Prize in 2016.
Our final question for Andrew Wiles was whether he would have kept on working on Fermat's last theorem, even if he hadn't found a solution back in the early 90s. His answer was very characteristic of his approach to mathematics.
I'm not a person who gives up on a problem.
We hope you enjoyed this special episode of our podcast, which was a joint venture between the Living Proof podcast from the Isaac Newton Institute and the Maths on the Move podcast from plus.maths.org. You can find out more about Fermat's last theorem by going to plus.maths.org/Fermat.
This podcast was produced by me, Rachel Thomas, Marianne Freiberger and Dan Aspel. Thanks for listening and bye for now.